In software engineering, we are taking chapter number 30, Product Metrics. Class-oriented metrics. The mood metrics or mood metrics suite. Now this MOOD stands for Metrics for Object-Oriented Design. So we will get the number, the quantitative measure for the design, and this is suite. That is, this is not one metric. The first metric is method hiding factor. The second one is attribute hiding factor. Third one is method inheritance factor. Fourth is attribute inheritance factor. Then we have the coupling factor, and finally the polymorphism factor. So two of them we are going to see. Now Harrison, Council and Nithi, they proposed metrics that provide a quantitative indicators for object-oriented design characteristics. That is, we are going to get the numbers, and numbers we can very well estimate. So a sampling of this mood matrix, let us take the method inheritance factor. This one we will take, and we will take the coupling factor. So method inheritance factor, here it is all about inheritance and method. In class based, in object oriented paradigm, we are talking about methods which is inside the class, and inheritance is how the attributes and operations are inherited by a different class. So degree to which the class architecture of an object-oriented system makes use of inheritance for methods, which we also called as operation, and attribute is defined as. How do we define this MIF? We define this MIF by this expression. This is the summation of MICI, this I, all I are the subscript, divided by sigma MACI. Now this summation, sigma will start from somewhere and it will end to somewhere. So sigma will start from 1 till TC. What is TC? Total number of classes. So TC is defined as the total number of classes in the overall structure, which is the architecture of the software, that is the design. Okay. Now this CI, what you see here, is a class in this architecture. So this MACI, which is the denominator, how do we define it? And even the numerator also will see. Actually the denominator is MDCI plus MICI. This MA, MD and MI, this is also class. C is the class we are referring to, because there are some different classes. So MA is number of methods that can be invoked in association with this class. So we are talking about association with CI. MD is the number of methods declared in the class, and MI is the number of methods inherited, not overridden in the class. Let me show you what is this inheritance and overriding. See, this animal class is there, and it has some attributes and say functions. Now dog is extending or inheriting the animal. So all the content has come, data, one, move, eat. So this is inheritance, simple inheritance. But if dog wants to make its own implementation for the function, say move, so this move, the function being newly implemented by dog, not use the previous one of animal, this is called the overriding method. So inheritance, of course, it is already there with dog, others. What I'm trying to suggest here is, we have a base class, we have a derived class. So all the content of base class will come to the derived class if it is in the public domain. Of course, the private won't come. And other function which are inherited can also be overridden. So these are the values. So the MIF value will tell you, it will indicate the impact of the inheritance, because all these parameters we discussed, it is all about inheritance. In this mood matrix suite, we have coupling factor. The matrix suite has 6 of them. So we are taking one of them, which is coupling factor. This metric coupling factor was proposed by Mood, and this is actually a ratio. But before we go ahead, this is coupling. These are different module, or these are different components. There is no coupling at all in the first case. Here there are certain dependencies between the independent modules, but here we have many dependencies. So these 4 are highly coupled and we don't want it. So as I was saying, the ratio of coupling involved between the classes, that is what coupling factor finds out. So the ratio of coupling is evaluated using a fraction. And what is the numerator here? See, just understand the formula. This, in the formula, this CF is the coupling factor, sigma I, sigma j. Now sigma is the summation. It will start from I equals 1 till the TC. TC is total number of classes. Total number of classes in your discussion. Now is client. What is this is client? Is client, and in the bracket we have Ci, Cj. Is client. Ci, Cj. So there are 2 different classes. Now this whole result will be 1. It will be 1 or 0. So it will be 1 if and only if a relationship exists between the client class and the server class. Client server classes are not equal. If one is a client of other, it will be 1. If it is not a client, if there is no relationship between the client class and the server class, then we say it will be 0. So the numerator can only be 0 or 1. So the ratio of coupling is evaluated using a fraction. Here you see the numerator. It is representing the total number of non-inheritance couplings in the module. Okay. And what are you getting in the denominator? The denominator signifies the maximum number of coupling that is possible for the corresponding module. TC square minus TC, which is the square of the total number of classes and subtraction with total number of classes. Okay. So this is how we find out the mood metric coupling. So this is all about how much different modules or classes they are coupled, or the functions inside the classes or the modules, they are interconnected. So as the value of this coupling factor will increase, the complexity of the object-oriented software will automatically increase. But the understandability, the maintainability, and the potential for reuse, it will decrease. It may suffer. So we need coupling as least as possible. Object-oriented matrix proposed by Lawrence and Kidd. Okay. Now Lawrence and Kidd, they divided the class-based matrix, object-oriented matrix, into 4 categories, and all have relationship or bearing on component level design. And these 4 categories are size, inheritance, internals, and externals. What is size? The size-oriented matrix for this they proposed by Lawrence and Kidd for an object-oriented design focus on counts of attributes and operation. So this is a class. These are the attributes, and these are the function operating on these attributes. So the counts of attributes and operation for an individual class. This is size-oriented matrix. Inheritance class, inheritance-based matrix. This works on operation which are used through the class hierarchy. That is, one class inherit the other class. Then it is actually using or reusing the methods which are defined or implemented in the base class. Then the class internals. This class internal matrix, they are talking about the cohesion and code oriented issues. So if we are talking about a class, does this class do all the like-minded, single-minded, one-point oriented work? The external matrix is talking about coupling and reuse. Coupling means two modules, how much interaction they have. So let us take the example of these metrics which are proposed by Lawrence and Kidd. The first one is the class size. Now the overall size of the class, how can we determine it? We have certain measures. Operation, the total number of operation. It can either be inherited or it can be private also, encapsulated within a class. That is the functions. Total number of attributes, again both inherited and private, encapsulated by the class. You can say total number of operation and total number of attribute count in the class. So this is the class size. So large values of this class size will indicate that a class may have too much of responsibility, and that is going to reduce the reusability of that class. And when you are going to implement and test, it will be difficult. It will complicate the things. Inherited or the public operations and the attribute should be weighted more heavily in determining the class size. Okay, because mostly the functions or attributes which are inherited in the different base classes, that has to be weighted more. The private operations and attributes, this will enable the specialization. Why? Because it is more specialized. It will not be inherited, it will not be used anywhere else. So they are more localized in the design. So averages of the number of class attributes and operation we can compute, and if you have a low average values of this class size, more likely that classes within the system can be reused. They can be reused in other projects or in this only. Operation oriented matrix. Operation is all about the function, the procedure, whichever way you call it. The operation or the function are working on the attributes in the class which are being encapsulated. So whenever we talk about the object oriented system, we generally talk about class. Other things we don't talk. So there are metrics which are proposed mostly on the class basis, not about the operations in the class. So Churcher and Shepard, they discuss, for example, just write a function. The method tend to be small, both in terms of number of statement and in logical complexity. This suggests that connectivity structure is more important than the content of modules. So what is inside the module is not that important. The connectivity structure of these methods inside a class and outside the class is more important. However, we can gain insights by examining the average characteristics of a particular method or operation. So there are three simple metrics proposed by Lawrence and Kidd. How to examine the average characteristic of methods and the operation present in the class. The first one is average operation size, OS with the subscript average. Now size can be determined how? By counting the total line of code, LOC. For example, this is a function. So we can compute or count the line of code and the number of messages sent by operation. How do we send the message and get the message? Through the function interface. That is the input parameter and the output parameter. So as messages sent by a single operation increases, the responsibility is not being properly allocated within a class. There is only one function is doing a lot of work. The other function are not doing that much of work. Operation complexity, OC. Now the complexity of an operation, this can be computed how? Using any complexity matrix like the cyclomatic complexity. So designers should see and strive to keep this operation complexity as low as possible. And then comes the average number of parameters per operation. So in an operation, in a method, how many parameters are there? The input parameters, the output parameter. Larger the number of operation parameter I am talking about this, the more complex the collaboration between objects will be there. So the input parameters, output parameters, they have to be as less as possible. So the MP average should be as least as possible. Metrics for source code. Now the programmer and software team, they are more interested in the software code. Now Halstead, he gave a theory of software science, and he was the first to propose the analytical laws for the computer software. So the Halstead, he assigned certain quantitative laws to the development of computer software. From A to Z, he said we can compute it, and we can do it using just the primitive measures. Only the code, that is, even if the code is generated or even the design has been completed, we can compute so many things, almost everything, using this Halstead theory. And the basic measure, which is, or the basis of Halstead theory or source code matrix, is how many number of operator and operands are there. I'm just writing a very naive code, easy code, and I'm just trying to point out what are the operator and what are the operands. Please remember, operators are all those symbols which are provided by the programming language, and operands are all those which a user has used, he has given, he has defined, he has declared. So if is an operator, braces operator, round bracket operator, angle bracket operator, double quotes operator. Okay, what are the operands? X operand, 5 operand. These are given by S. So we will just count them. This will be N1, number of operator, number of operands, N2, capital N1, capital N2. Now just write them and remove the duplicates. Just count. If you have multiplicity, just count 1, and that will come from N1 only. So N1 will get reduced to small n1 because we have just reduced the multiplicity. Count the operator, remove the duplicity or multiplicity, you will get N2, number of distinct operands that appear in a program. So Halstead used these parameters to develop expressions for the overall program length, potential minimum volume for an algorithm, the actual volume in terms of bits, the program level, that is the complexity, the language level, which is constant for like COBOL or C or C++ or C#, then development effort, how much effort will be required, what will be the development time, and the projected number of faults, problems in the errors. So he gave these all expressions. So this is the basis. I told you this has come from simple code or the algorithm. So he said the length of the code will be n1 log n1 plus n2 log n2. These are all small logs. Basis 2. Program volume will be capital N we have found out, and then log n1 plus n2. This is log base 2. And V, capital V, which is the volume, will vary with the programming language, and this will represent the volume of information in bits. So minimum volume should be there for a particular algorithm. He also said volume ratio, which is actually the one inversion of your difficulty. So this is the ratio of volume of most compact form of program to the volume of the actual program. So if you have a very good program and the actual program, that is the compact program divided by the actual program, this is the volume ratio. L, this is volume ratio, has to be less than 1. This is the volume ratio, 2 by small n1 into small n2 by capital N2, and you just invert it. Just do 1 by L, you will get the difficulty. So this difficulty and volume, when you multiply, you will get the effort. Effort will be V into D. So this is how various parameters. Also, I tried to show you on the right side bottom. There are various ways you can use expression to find out. We'll take the example also. We are taking an example of Halstead's matrix. Various things we can estimate or find out using Halstead matrix. So we have taken an example, very small code. So we have to find out the operators and operands. Every formula is dependent on these values only. Small n1, small n2, capital N1, capital N2. So first of all, what are the operators? Operators are all those symbols or notation which are provided by the programming language. Those which we are giving are called operands. Okay. So we will make a list of operators and then operands. First of all, let us start with the operators. If is the operator, round bracket, then angle bracket, then round bracket close, curly brace, if, round bracket again, angle bracket, then round bracket close, is equal to, then star, that is the multiplication, and semicolon, and the braces. Okay. Now you have to count it. How many are there? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So this is the 13. These are the total number of operators, and that is the capital N1. Okay. Capital N1 is the total number of operators. Let us go to the operators. Operands. Operands are those which are given by us. So K, then 2, then K repeated. Don't worry about repeating. Then we have 3. Then these are constant and variable basically. X, then again X, and then we have K. So these are the number of operands. How many are these? Just count it. They will be 7. So number of operands are 7. N2 is 7. Capital N2 is 7. Now the question will be, what is small n1 and small n2? These are distinct operators and operands. So now just you have to remove the duplicacy or multiplicity. So small n1 will come from this first column. First column we have used. So if is already there. So one I have crossed and other I have just removed because it is repeating. Round bracket also repeating. Angle bracket is not repeating. And then we have a round bracket. This also is repeating. So I am removing one of them. Curly brace. No, all these are distinct, unique. Now I just have to just mark it with a line and just calculate how many lines are there. Okay. We have just removed 3 of them. 3 are the duplicates. So just cross it and just count how many lines are there. These are 10. So 10 is the distinct operators. I have just removed the duplicacy. The same thing we have to do for the operands. Now this K is repeating. This is also repeating. 3x is repeating. Okay. So K repeating. So 1, 2, 3, 4. How many are there? Small n2 is 4. Okay. Now these values will be put and all the formula, they have these content only. These notations only. Calculation I have already done. So I will tell you what is the logic here. The first thing we will find is the length. Length is capital N. Length is denoted here by capital N, which is equal to capital N1 plus capital N2. So what are the values? We know already 13 and 7. So you just see here N1 plus N2, 13 plus 7 is 20. Now coming to vocabulary. Vocabulary is small n. Vocabulary is small n and this will be computed by small n1 plus small n2. This will be small n1 plus small n2. So small n1 is 10, small n2 is 4. 10 plus 4 is 14. So this is the computation of vocabulary. Then the estimated length. This is represented by n cap, estimated length, n cap. So this will take some time. N cap will be small n1 log base 2 small n1. So n1 log base 2 n1 plus n2 log again base 2 N2. Okay. Now only thing of concern here is, let me show you the computation. So N1 you know it is 10, N2 you know it is 4, but log is base is 2. So we have to convert this log base 2 to log 10. So log base 2, most of the scientific calculator you won't be able to calculate. For that you have to change the log to base 10. For that just change the base 10 and just divide it by 0.3010. So log 10, see the base I have changed and just divided by 0.3010. And log 10 is 1 and log base 10 of 4 is 0.6020. Computed it will be 41.222. Next thing will be purity ratio. Purity ratio will be this n cap which we have just calculated, estimated length, divided by capital N. N cap was 41.222. And what is the capital N? Capital N is 20. So this is the computation. Purity ratio is, it will be 2.0611. Next thing is program volume, or it is volume. So volume will be capital N, log base is 2, and then we have N1 plus N2. These are small n1 and n2. So 20 is capital N, log is base 2, n1 plus n2 we have already computed, it is 14. So as I'm saying that you have to change the log base 2 to log base 10, just divide it by 0.3010, 76.154 will come. Now volume is there, not difficulty. The difficulty will be small n1 by 2 into capital N2 by small n2. Capital N2 by small n2. Okay. Now you see here, n1 is 10, capital N2 is 7, small n2 is 4. So it will be 8.75. Now let me tell you one more thing. Here is one more thing which is called volume ratio, VL. Volume ratio. This is 1 divided by difficulty. Just divide difficulty by 1 and you will get the answer. Effort is simply volume into this difficulty. So 8.75 is the difficulty. Volume we already know, 76.154. The answer will be 666.3475. So this is how we calculate the Halstead matrix. These are all the basic thing is number of operators and operands and discrete operands you have to find out. Metrics for testing. So the majority of the metrics which we have seen for testing, they focus on the process of testing, what process are being adopted, but not on the actual technical characteristics of the test themselves. So tester has to do what? They have to rely on the analysis, design, the code metrics, for design and execution of the test case. So they have to rely upon all these. So the architectural design metrics provide certain information to us, like architectural design we have already seen. So what are the metrics? What information do they give? They give us information like ease or difficulty for integration testing. Do we need stubs and drivers, like the need for the specialized testing software? Do we need a main dummy program or the sub-module dummy programs? So this architectural design matrix will tell you. Along with this, the architectural design matrix gives certain more things. The cyclomatic complexity also, it will give you how much extensive unit testing you have to do. If you have high cyclomatic complexity, likely the module is error prone. So using the definition of the program volume and program level, we have already seen about Halstead matrix. When we apply it to the testing, so Halstead gives us the effort. We have volume and we have the program level. He says the program level is 1 by n1 by 2 plus n2 by n2. This is nothing but the L, the volume ratio. And this is program 1 by, because this is nothing but what? This is nothing but difficulty. As I said, difficulty and volume ratio are inversion of one another. Effort, E is effort. Effort is E, V is volume, D is difficulty. So if you multiply PL multiplied by effort will give you volume, or you can say effort is volume into the D, difficulty. Now this can be used to find out the effort, but this can be done for the whole software in terms of testing. How much effort you are going to put in. So the percentage of overall testing effort for a certain module K, now with the Halstead matrix, can be computed like this. So this is the percentage of testing effort, and this is given by EK divided by summation of EI. This numerator is computed for module K for each module, and the denominator sigma EI is the sum of Halstead effort across all modules of the system. How many modules? 10 modules. So you have to do sigma 1 to 10. And this is for the module which is concerned, which we are talking about. So this is the percentage of testing effort. Metrics for maintenance. Now whenever you deliver the software or you give various versions, then there will be maintenance. That is, module will be changed, something will be modified. So IEEE standard 982.1/2005, they suggest the software maturity index. It indicates stability of a software product, and this is based on the changes, modification that occur for each version or release of the product. So the changes and modification, maintenance is all about this only. So there is version 1, there can be version 2, there can be multiple version. Every time there will be some module change, there will be some module added, there will be some module deleted. This software maturity index is computed very easy. There are a parameter MT is number of modules in the current release. It can be any version, any release. FC is number of modules in the current release that have been changed. What is FA? See, this is the number of modules in the current release that have been newly added, extra added. FD is the number of modules from the preceding release that were deleted in the current release. So that is the number of modules being deleted. So the SMI is computed like this: MT minus FC plus FA plus FD divided by MT. As this SMI approaches 1.0, we can assume that the product is beginning to stabilize. SMI may be used for planning software maintenance activities. The mean time to produce a release of a software product can be correlated with SMI, and empirical models for maintenance effort can be developed. Okay, this is all about this discussion. Thank you so much and take care of yourself.